welcome back. So now we're going to be talking about reduced row echelon form, which is going to make matrices do a little bit more work for us and help us get right into our answer. So what's different between reduced row echelon form and row echelon form? Well, actually, as the name implies, reduced row echelon form, or RREF for short, means that we're going to reduce our row echelon form down one step further. And that one more condition is this. So our fourth condition is that each pivot is not only the first non-zero term in its row, but it's also the only non-zero term in its column. So with this, we look at our final matrix that we left off with. We write it down into RREF. We see that this pivot here is not the only non-zero term in its column, and similarly with this pivot. So we are in reduced row echelon, we're in row echelon form, but not reduced row echelon form. So once again, we can use our row operations to solve the mystery of this linear equation as to what x, y, and z simultaneously satisfy all three equations. So to do that, let's do some more row operations. So we're going to take this matrix and we want to get these both to be 0, correct? So we can actually just do these two operations at once. It'll save us a little bit of time and effort. So we want to get this 2 to be a 0. We also want this 1 to be a 0. So we can take row 3. We can multiply it by -2 and add that to row 2, and that'll become our new row 2. Similarly, we can take row 3, multiply it by -1, and add that to row 2, or row 1, and that will become our new row 1. So if we see how we did this, so we'll see our new matrix here. We're not doing anything to row 3, so we're just going to copy that back on in here. However, we are doing some things to row 2 and row 1. So we're taking -2 times row 3 and adding it to row 2, and that's going to be our new row 2. So 0 times -2 is 0. 0 times -2 plus 1 is going to still be 1. 1 times -2 plus 2 is going to be 0, which is exactly what we wanted, so we're good on that one. And then -2 times 6 plus -1 is going to give us a 12 minus 1, 11. And then finally, for row 1, we're taking row 3 and adding it to row 1. So 0 times -1 is 0, plus 1 is 1. 0 times -1 plus 1 is still 1. And then -1 plus 1 is 0, which is exactly what we wanted, so we're in business. And then lastly, -6 times -1 is 6 plus 0. That's going to give us a whopping 6. Okay, now, are we in reduced row echelon form yet? Not quite. This pivot is not the only non-zero term in its column, so we need to get rid of this one right up here. So to do that, we're going to take row 2, we're going to multiply it by -1 and add it to row 1. We're going to store this here in row 1. So we're not doing anything to row 2, so we can just copy that one back on in here. Similarly, we're not doing anything to row 3, so once again, just copy that back on in here. And then row 1, we are going to be taking row 2 and adding it to row 1. So 0 times -1 plus 1, 1. 1 times -1 is -1 plus 1 is 0. Yes. 0 times -1 plus 0 is still 0. 0 or -1 times 11 is -11 plus 6 is going to give us a -5. So now, are we in reduced row echelon form? Why, yes, we are, because we don't have any rows of all zeros, so we don't have to worry about that condition. Our second condition, where each pivot equals 1, we see each pivot equals 1. Third condition, each pivot is further to the right than each pivot before. So this pivot is further to the right than this one. This pivot is further to the right than this one. So we are in business with that one as well. And then our last condition, that each pivot is the only non-zero term in its column. There we go. And we are done. So then we're going to see this. X equals -5. Y equals 11. And then Z equals -6. So then our final solution, once again, is going to be 5, 11, or -5, 11, -6. So if you recall, this is the same solution we came up with when we used row echelon form and back substitution. So this just takes our matrix one step further and gives us the correct answer. So now let's go back and try another example of using reduced row echelon form to solve the mystery as to what x, y, and z are in a linear system. Okay, so for our next example of reduced row echelon form, RREF, we will be working with this linear system. So when we make our matrix, or augmented matrix, we're going to have this little number here. So we now have this augmented matrix, and we want to get it in row echelon form. So our first operation is that we're going to want to get these two elements in the same row or the same column as one disappear. So what we can do is we can take -3 times row 1 and add that to row 2 and make that our new row 2. And we can also take negative row 1 and add that to row 3 and store that right on in row 3. So let's go ahead and do that. We are not doing anything with row 1, so we can go ahead and keep that the same. And then our second column here, or second row here, we're taking -3 times row 1. So -3 times 1 plus 3 is 0. -3 times -1 is 3, plus -3 is going to give us a 0. -3 times 2 is -6, plus 6 is 0. Do you notice anything suspicious starting to happen? And then -3 times 5 is -15, plus 15 is also 0. Okay, so we have a whole row of zeros, so we know we're going to have to do something about that because we have our first condition. But first of all, let's just go ahead and make sure we get row 3 on in here as well. So -1 plus 1 is 0. -1 times -1 is 1, plus 1 is also 0. And then -1 times 2 plus 5 is 3. -1 times 5 is -5, plus 2 is going to give us a -3. Okay, now all we have to do is take this matrix and make sure we're not violating our first condition. So how we can do that is we can do a good old swap-a-rooney once again on rows 2 and 3. So row 2 is going to become row 3, and row 3 is going to become row 2. So once again, we're not doing anything with our first row, so we'll just copy that back on in there. And then our second row is going to become our third row, and our third row is going to become our second row. Okay, so now what we want to do is we want to get our pivot in this equation, on this second row, to be equal to 1. It doesn't matter that it's not in the second column, because as we'll see, we can still get a solution of sorts even though we don't have a pivot variable in the second column. So don't worry about that. All we have to do now is make sure that our pivot that we do have is equal to 1. So we're going to take 1/3 row 2 and put that back in row 2. So once again, we're not doing anything to change our first row, and we're not doing anything to change this lovely row of zeros at the bottom. All we're doing is changing row 2. So we're going to have here, after you divide everything in that row by 3 multiplied by 1/3. Okay, so now we have this matrix. Is this an REF yet? Yes, it's an REF, but is it an RREF? Nope. So all we have to do still is make sure that this pivot variable is the only non-zero term in its column. So how we can do that is we can multiply row 2 by -2 and add it to row 1. So let's do that on over here. So we're taking -2 times row 2 and adding that to row 1, and that's going to be a new row 1. So we're not doing anything to change row 2. We're not doing anything to change our lovely row of zeros at the bottom. And then we are doing something to change our first row. So let's do that operation. So we have -2 times 0 plus 1 is going to be 1. -2 times 0 plus -1, still -1. -2 times 1 plus 2 is a 0, exactly what we want. And then -2 times -1 plus 5 is going to give us a 7. So now, is this in our REF? Are all 0 rows at the bottom? Check. See the 0 rows all the way at the bottom? Each pivot equals 1. Okay, so the first non-zero term in this is equal to 1. First non-zero term in our second row, equal to 1. We have no non-zero terms in row 3, so we are set on condition 2. Condition 3, each pivot is further to the right than the pivot above. This is way further to the right than this one, so we are set. And then each pivot is the only non-zero in the column. So true for this pivot and this pivot. So now we have our answer. So now let's actually use our matrix vector form to see what our answer is here. So we'll have this matrix. This is just our new and improved coefficient matrix times our variable vector. And that is going to be equal to our new and improved B. Just like that. So now we're using our matrix vector form again. Do our matrix multiplication on this side. So we have 1 times x plus -1 times y. So we have x minus y. 0 times z is 0. So that's going to be equal to 7. Okay, and then we're going to have 0 times x plus 0 times y plus 1 times z. So we know z is equal to -1. And then, oh, should be a 0. And then 0 times 0, 0 times 0, 0 times 0. You know, Joe, we're just going to end up with all zeros for our last one. So then we end up with this as our solution. What could this possibly mean? This means that we have infinitely many solutions. Okay, so does that mean that we have any number for x, y, and z will work? No. Actually, our solution is any point on the line x minus y equals z that's on the plane z equals -1. So basically a general thing of our general solution to this is going to look like this: x, y, -1, where x and y are from the line y equals, I'm just going to put this in slope-intercept form here. So you can actually find any two numbers that satisfy this line here, and then just have z be equal to -1, because that's the plane that this line is in. So we have infinitely many solutions, but only along this line here. So now we have successfully solved 2 linear systems in reduced row echelon form using our row operations. So we are almost linear algebra experts, but we have a lot of exciting things coming. So now just enjoy basking in knowing how to use row operations to solve the mystery. So we'll see you later.